Welcome to EDU World Space.
In this problem, on the topic of mechanical vibrations, we are told that a motor having a weight of 40 pounds is supported by 4 springs. Each spring has a spring constant of 225 pounds per inch. The motor is constrained to only move vertically, and we know the amplitude of this motion to be 0.05 inches at an angular speed of 1,200 revs per minute. If we are given the weight of the rotor to be 9 pounds, we want to determine the distance between the mass center of the rotor and the axis of the shaft. So we are given the weight of the motor W to be 40 pounds, and we know that each of the 4 springs has a constant of 225 pounds per inch. The motor is constrained to move vertically, and the total effective spring constant is 4 times the spring constant of each spring, 225 pounds per inch, which gives an effective spring constant of 900 pounds per inch, which is 10,800 pounds per foot. Now we can find the natural frequency, the natural circular frequency omega n, and this is the square root of the spring constant K divided by the mass m. And so this is 10,800 pounds per foot divided by the mass of the motor, which is its weight 40 pounds divided by 32.2, which is g, and this gives us the natural frequency of 93.242 radians per second. We'll keep as many decimal points for accuracy. Now, if we have the angular speed of the motor omega to be 1,200 revolutions per minute, we can calculate this to be 125.664 radians per second, and we have x to be the xm, the maximum position or the amplitude of oscillations, to be 0.05 inches. Again, we can convert this to feet. So 0.05 inches is 4.1667 times 10 to the minus 3 feet. So now we can use our equation that relates all these variables, and we have xm to be the periodic force Pm over k, all divided by 1 minus omega over omega n, all squared, which means therefore that we can find Pm over k by rearranging this equation, and we get Pm over k to be xm into 1 minus omega over omega n, all squared. And so now if we substitute the values in, we get 4.1667 times 10 to the minus 3 feet into 1 minus 125.664 divided by omega n, which is 93.242, and that's squared. And so computing this, we get Pm over k, which is the force over the force constant, to be minus 3.4015 times 10 to the minus 3 feet. And this is out of phase. So This means that this force PM is equal to 10,800 pounds per foot multiplied by 3.4015 times 10 to the minus 3 feet. And this gives us PM to be 36.736 pounds of force. Now, for an unbalanced rotor with weight 9 pounds, rotating at 1,200 revs per minute, with the mass center at a distance r from the axis of rotation, we have this periodic force PM is equal to the mass of the rotor mr times the mass center r bar times omega squared, which means r bar is equal to PM. R bar is what we want to calculate, and that's PM divided by mr times omega squared. So if we substitute our values into this equation, this is 36.736 pounds from above divided by the mass of the rotor, which is its weight 9 pounds, divided by 32.2 times omega squared, which in radians is 125.664 radians per second, all squared. And so calculating, we get the mass center distance to be 8.3231 times 10 to the minus 3 feet, which in the units used in the problem is 0.0999 inches.